Good afternoon, this is Stuart Ballantyne from Australia, and thank you for viewing my presentation, which is Unsinkable Vessels, the ultimate pursuit. We're looking at the problem, which is the risk of damage stability and survivability. And as we can see in the shot, this happens to many vessels, large and small. So the basic naval architecture of this is pretty simple. The basic principles of gravity, weight, for instance, 1,000 tons. It's heavy, but it'll fall in exactly the same way as an apple, as described by Sir Isaac Newton at the age of 24. But the weight will sink unless it's supported by 1,000 tons of buoyancy. And this was courtesy of Mr. Archimedes of Greece, 212 BC. So I'd like to talk about permeable volume. 1,000 tons is supported by a submerged air bubble, if you like, displacing the equivalent of 1,000 tons. What would happen if this watertight integrity is lost? I'd like to come on to permeable volume. Permeable volume is the internal space in the ship hull and superstructure available for flooding. So the ship performance is functionally and safety are dictated by the external shape, the deadweight permeable volume, and the distribution. But in case of flooding accident, the amount and distribution of the residual permeable volume dictate whether the ship may sink or capsize. Yet this is all calculated to extreme accuracy, while permeable volume and its distribution is calculated with naive approximation. We are told by the various authorities, flag authorities and classification societies, the permeable volume of the engine room shall be such and such, and when you ask the question, no one can tell you why that number is there. We've been working on deployable bulkheads. These are instant bulkheads. It's not the subject of this paper, but we can actually put deployable bulkheads which come down within 3 minutes, and we can inject foam into these deployable bulkheads, which makes them fire tight and watertight. Now, the advantage on military vessels and operational vintage vessels can be seen. It's excellent. So this overcomes problems to the insurance, financiers, and regulatory authorities. So if we move on just to the passive protection, which is really the subject of this, the risk control options must be built into the design, and they'll offer instant residual uprighting moments and evenly keeled trimming by foam around the perimeter of the vessel. So it transforms unutilized spaces into a significant asset with regards to the vessel damage stability. So this acts to reduce the permeable volume and the flood water mass accumulation. So it improves the survivability index, and the survivability index is defined as the number of cases in 100 disaster scenarios that a vessel can survive. So I'm going to give you some examples. This 50-meter catamaran in the Bahamas ran into a rock during the night at 15 knots, damaging both bulbs. The watertight bulkhead remained intact, but the result was water ingress into the forepeak port and starboard, trimming of the vessel by the head by 800 millimeters or 2.5 feet, raising of the stern by a similar amount, exposure of the upper sections of the 4 propellers and the 2 rudders, and due to the relatively benign weather conditions at the time and mid-load condition of the vessel, she managed to inefficiently propel her way back to Nassau. So we investigate the advantage of filling the 4 peak tanks of coastal vessels with class-approved closed-cell foam in terms of stability, trim, and survivability. So the next slide shows that if we fill this 4 peak tank, including the bulbs, and if their bulbs are then damaged, no water will ingress. There will be no trim by the head. There is no need for a collision bulkhead to come higher than D, a draft plus 0.5 D. In this case, it's a 2-meter vessel, 2-meter draft vessel, so it's 3 meters above the baseline. There is no need for the collision bulkhead to remain between 0.5 and 0.15 of the waterline length. And in the case shown, we can actually move the bulkhead to frame 38, which could be under 0.05 L. So in preparation of areas like this, to get people in to prepare the welds and everything else is very difficult, it's costly, ventilation is dangerous, and future surveys in these areas is restricted to skinny surveyors. And upgrades to the coating of these spaces is quite expensive. This is what it looks like brand new. This is in a forepeak of one of our cats. And 12 years later, this is quite often the site in a forepeak, and this is taken from a 50-meter landing barge, the forepeak tank in there, which is a result of condensation corrosion from the deckhead, water corrosion, salt water from the anchor chain, and ballast water. In this particular case, it cost $69,000 to repair this particular compartment. So the advantage of thermal foam buoyancy is that it can reduce the areas for ventilation, so it improves the heating and the cooling. So if I take a vessel like this and I add buoyancy forward, most 2-compartment subdivision vessels will have a survivability index of 0.7, or 70 out of 100 disaster scenarios will survive. If I put foam in the forepeak as shown, it'll move the survivability index to 0.75. If I do the aft end, it's 0.82. Under the floor of the cabins, it's 0.94, and across the bridging structure, it's 1. So looking at transversely, 0.94s are under here, and unsinkable is there, and also the deckheads are insulated with open cell foam. So is the vessel the best lifeboat? Is the ship itself or the vessel the best lifeboat? So that's the question that has to be asked. So we forensically look at all of the ways of keeping these vessels afloat. So the question is, if you knew this vessel had a survivability index of 100, in other words, it was unsinkable, would you jump off this ship, a 150-meter ship, and jump into a 5-meter life raft or an 8-meter lifeboat? And the answer is you would not. And abandoning any ship in rough seas has an appalling track record of serious injuries and loss of lives. In the Fastnet yacht race in the UK, 1979, 80% of the abandoned yachts didn't sink, and there were 19 people lost who left these yachts. 1998, the Sydney Hobart, there was 6 people lost. You might say, well, what about fire? But the latest incidents show a decreasing number of fires in passenger vessels due to longitudinal subdivision of the fire sections, fire protection. So if you have an unsinkable vessel, do you then need lifeboats and davits with 700,000 each, 6 tons at a very high VCG, marine evacuation systems, plus the ongoing repairs and maintenance cost of these, plus the crew to help you evacuate? That's an ongoing cost, and it's a basis of manning for most statutory authorities. So the concluding remarks is an unsinkable vessel is the best lifeboat. We can achieve unprecedented levels of safety and survivability, plus improving the acoustic and thermal insulation. The build's pumping system can be reduced significantly. The capex can be saved on internal coatings. Repairs and maintenance can be reduced for underdeck void spaces susceptible to corrosion. We can improve the lifespan of all commercial vessels, and we can get insurance premium reductions. This in turn raises societal expectations for marine safety enhancement, fueling that virtuous circle that will close only if ships are designed, built, and operated with zero risk tolerance, i.e. unsinkable vessels. Ladies and gentlemen, thank you for your time. Please feel free to ask me any questions.